This video is about complex number. I will divide this video into two parts. The first part is about the complex number and its calculation. And for the second part later, I will talk about complex number in polar form. So let's start with the first discussion about the complex number itself. What is complex number? Complex number is the number that contain the imaginary parts of a number. So as we know that number can be a real number and can be an imaginary number. The number that contain both of these is called the complex number. So from the definition, if we have a square number of negative, so x squared equals to -1, we sometimes say it, oh, there is no real roots. There is no square root of negative number. Yes, because the result is not real. But now, to accommodate the needs of the root of negative, so we have to express the number into the complex number. So we can define the square root of -1 as I. So we can express that the complex number is denoted by z equals to x plus iy, where x is the real part and y is the imaginary part. You can see from here. The number alone is the real part, and the number with I is the imaginary part. Yeah? For example, if I have 3 and 4i, so that means the 3 will be the real number, and 4i is the imaginary number. Now, what can we do with the calculation including the complex number? Complex number can be added and subtracted. So complex addition is defined by separately adding the real part and the imaginary parts. So if I have two complex numbers, z and w. So if we have two complex numbers, z and w, with z equals to a plus bi, and w is c plus di, then the addition of the two complex numbers is adding the real parts and the imaginary parts separately. So we add the real part and collect it into the real parts. And then for the imaginary parts, we collect it together as the imaginary parts. So this will be the real and imaginary parts of the new complex number. For example, 3 plus 5i plus 2 minus 3i. So we can just add the real part, 3 plus 2. This is the real part. And then we add the imaginary parts together. So 5 minus 3i. So the result is 5 plus 2i. B, 3 plus 5i plus 6. 6 in here is the real part because 6 plus 0i. So we can classify, so 3 plus 6 And then for the imaginary will be 5 plus 0. So 9 plus 5i. The next one, 7i is the imaginary part, so it be 0 in the real parts. So we can just combine 0 minus 4 plus 7 minus 5i. So negative 4 plus 2i. That's it. That's for addition and subtraction. The next calculation is multiplication. We have to remember that I is the square root of negative 1. So I squared will be equals to negative 1. So let's see example number 8. We can just do the algebra multiplication as usual. So this is 6 plus 12i. For B, we do the same thing. So this is become 5i plus 3i squared. And remember that I squared equals to negative 1. So this will become 5i minus 3. Or I can rewrite as negative 3 plus 5i. See, we do the calculation expansion as usual. So this is 6 plus 8i minus 21i and minus 28i squared. So simplify. So we will have 6 minus 13i minus, in here we have I squared, so it becomes negative 1, so plus 28. So we will have 34 minus 13i. Next, for the division, we cannot have the complex number and the denominator. So we cannot divide the number by complex number. So we need a help of a number to remove the complex number in the denominator as a divisor. So that number is called as a complex conjugate. So what is the complex conjugate? The complex conjugate is the complex number that has the different sign of the imaginary part. So if the complex number is a plus bi, so the complex conjugate, the symbol is this, is a minus bi. So the difference is only the sign of the imaginary part. Any complex number, a plus bi, always has a complex conjugate a minus bi. Some books has different symbol of complex conjugate. We have Z, so some books will use this symbol, and the other book maybe will use this symbol, but they are familiar. But commonly, most of the books are using this symbol. How do if we multiply the complex number and the conjugate? If you multiply it, you will have a real number. So that's why we can multiply a complex number with the conjugate to remove the complex number properties as a divisor when you divide a number by a complex number. In this case, we can see that Z times C conjugate is a plus b I times a minus bi. So this is a square minus abi plus abi minus b square I square. Since I square is -1, so I can have a square minus, we can cancel this, and then plus b square. So we can see that the multiplication between the complex number and the conjugate is a square plus b square, or this is the real number. You can see here a, so 1 divided by I. So to remove the I, we have to multiply it by I over I. So this is equals to I over I squared. So I squared is -1, so it's negative I. B, 3, 1 plus I. So we have to multiply by the conjugate. So 1 minus I over 1 minus I. So on the top, we have 3, 1 minus I over, this is 1 plus I and 1 minus I. So the result is 3, 1 minus I over 1 plus 1. So equals to 3 over 2, 1 minus I. And C, 4 plus 7I over 2 plus 5I. So we have to multiply by 2 minus 5I, 2 minus 5I. So on the top will be 4 plus 7I times 2 minus 5I. Well, so this will be a square plus b square. So 2 square plus 5 square. So the denominator will be 4 plus 25, it's 29. And the top will be 8 minus 20i plus 14i minus 35i squared. So again, simplify. I squared is -1, so it's positive 35. 8 plus 35 is 43 minus 6i over 29. Solving complex equation. We can solve complex equation by collecting the real parts and the imaginary parts separately, as we did before in the addition, subtraction, multiplication, and also the division. But there are some operations that we have to remember. Like if you multiply a z with the conjugate, as we have before, it will be the real numbers only. If you index the complex conjugate, it will be the same as the conjugate of the complex number. And then if you multiply two complex number and then you conjugate it, so that's the same result as you multiply the two conjugates. And also if you divide two complex number and then you conjugate it, so it has the same result as you divide the two conjugates. Sometimes we need these operations. Let's see the example. Solve each of the following equations for the complex number z. So for 1a, 4 plus 5i equals to z minus 1 minus I. So I can rearrange first. Z equals to 4 plus 5i plus 1 minus I. So z equals to, I can collect the real part, 4 plus 1 plus the imaginary part, 5 minus 1i. So 5 plus 4i. So this is the z. B, 1 plus 2i, z equals to 2 plus 5i. So to remove the complex number, I can just divide it. So 2 plus 5i over 1 plus 2i. And then to solve this, I have to remove the complex number in the denominator. So I multiply it with the conjugate, 1 minus 2i, 1 minus 2i. So this will be 2 plus 5i times 1 minus 2i over 1 square plus 2 square. So 2 minus 4i plus 5i minus 10i squared over 5. So this is 12 because 10i squared will be negative 10. So it will be positive 10. 2 plus 10 is 12. And then plus I over 5. Or the other method, I can multiply the complex number in front of z with the conjugate. So I multiplied both with the conjugates of the 1 plus 2i. So I can use the relation z times c conjugate equals to real number. So this will be 1 square plus 2 square times c equals to 2 minus 4i plus 5i minus 10i squared. So 5c equals to 2 plus 10, because this is 10i squared, plus I. So z equals to 12 plus I over 5. The same result. Number 2. Solve the following equation for real x and y. I. 3 plus 5i plus x minus yi equals to 6 minus 2i. So we can move all the numbers to the right. So x minus yi equals to 6 minus 2i minus 3 plus 5i. So x minus iy equals to 6 minus 3 is 3 and negative 7i. So that means x will be 3 and y will be 7. X plus iy equals to 1 minus I, 2 plus 8i. So x plus iy equals to 2 plus 8i minus 2i minus 8i squared. So this is 2 plus 8 plus 6i. So x plus iy. So that means x plus yi is 10 plus 6i. So x is 10 and y is 6. And then for B, determine the complex number z that satisfies z 3 plus 3i equals to 2 minus I. So I will multiply it with the conjugate, so 3 minus 3i. So this is multiplied by 3 minus 3i. So here it will become 3 squared plus 3 squared equals to 6 minus 6i minus 3i plus 3i squared. So z times 18 equals to 6 minus 3 minus 9i. So z equals to 3 minus 9i over 18. Or so it will be 1 minus 3i over 6. That's it. Square root of complex number. The square root of complex number is also a complex number. For example, find the roots of this. So that means the z is the square root of 21 minus 20i. So z squared is equals to 21 minus 20i. So I can just have x plus iy, z equals to x plus iy squared, yeah, equals to 21 minus 20i. So that means this will be expanded into x squared plus 2xyi plus I squared y squared, 21, 20i. So I squared y squared is negative y squared. So it's x squared minus y squared. I collect the real parts. And I have the imaginary part. So this is real, this is imaginary. 21 minus 20. And then I can construct the simultaneous equation. So x squared minus y squared equals to 21. And 2xy equals to negative 20. So that means I can have y equals to negative 10 over x. And then I can replace it to the first equation. So x squared minus y squared, negative 10 over x squared equals to 21. So I can just multiply it by the x squared. So it's x4 minus 100 equals to 20x squared. And it can perform a quadratic equation. So this is x squared minus 25 and x minus plus 4. So x squared equals to 25, x equals to 5, or x equals to negative 5. From here, x plus 4 equals to 0, so x equals to negative 4. In this case, this is non-real, so we can ignore this, because x and y here should be a real number. When you have z equals to x plus iy, both x and y should be real. So that means we can work on this. When x equals to 5, the y will be negative 2. Or when x equals to negative 5, y will be 2. So the two complex numbers, the roots of the 21 minus 20i, is z equals to 5 minus 2i, or negative 5 plus 2i. These are the square root. Next, complex roots of polynomial equations. We can find the roots of the polynomial equations in the form of complex numbers. First, using the quadratic formula. Complex roots always come in pairs. So the complex root and the conjugate. So this is always, so they are always in pairs between the conjugate and the complex number itself. We can find the complex root. You can use the long division method. We can use factorization, factor theorem, and vice versa as we solve the polynomial of the normal numbers. So for example, we can solve it quadratic equation z squared plus 4z plus 13 equals to 0. We can solve it like we treat as the quadratic equation, normal quadratic equation. So this is, can be, I can use the formula. So minus b, so this is a, b and c. So minus b plus minus square root of b squared minus 4ac over 2a. So negative 4 plus minus square root of 16 minus 52 over 2. So negative 4 plus minus square root of negative 36 over 2. So negative 4 plus minus root of 36 is 6, but negative 36 is 6i, because this is root of negative 1 times root of 36. So this is I, this is 6, so 6i over 2 equals to negative 2 plus minus 3i. So the solutions are z equals to negative 2 plus 3i, or z equals to negative 2 minus 3i. We can see that the complex root always in pairs with complex conjugate. Still that 1 plus I to the power 4 equals to negative 4. In this question, I can find 1 plus I to the power of square first. So if I expand this, so it will be 1 plus 2i plus I squared. So this is 1 plus 2i minus 1. So this is only 2i. So that means 1 plus I to the power of 4 is 1 plus I to the power of 2 squared. And this is equals to 2i squared. So this is equals to 4 times I squared. So negative 4 equals to left-hand side, proven. And then find all the roots of the equation z4 plus 4 equals to 0. So we know that 1 plus I is equals to negative 4. So I can say that z4 equals to negative 4. And from this form, we know that 1 plus I is one of the root, the complex root of the equation. So that means the other root should be 1 minus I, because complex roots always come in pairs with the complex conjugate. So from here, we can find the equation. So I can find z, find the factor, z minus 1 plus I times c minus 1 minus I. So I will have z squared minus 1 minus I z minus 1 plus I z by plus 1 plus I 1 minus I. So z squared minus 1, so it's minus 2 plus I minus I, so it's only 2z. And then from here we have 1 squared plus 1 squared. So this is 2. So that means the root of z 4 plus 4 is z squared minus 2z plus 2 times another root. So because this is z squared, z4, so this would be z squared squared. Because this is z4, so z squared times z squared plus az and then plus b. So we have 4 here, so that means 2 times b will be equals to 4, so b equals to 2. So the factors are z squared minus 2z plus 2, z squared plus az plus 2. Now find a. We can find the terms of z. So how do you find z? We can use z squared, yeah? So that means this is negative 2az squared. So we have to collect all the z squared. How do you make z squared? Plus 2z squared. And then plus and then plus 2z squared. So this will be equals to 0 because we don't have z squared in the equation. So that means negative 2a z squared plus 4z squared equals to 0. So negative 2a plus 4 equals to 0. So a is equals to 2. So that means the factors are z squared minus 2z plus 2 and z squared plus 2z plus 2. And we have to find the complex root from this. We can use the formula again. So z equals to minus b minus 2 plus minus square root of b squared minus 4 times 1 times c over 2. So this is negative 2 plus minus square root of 4 minus 8. So negative 4 over 2. So that means z equals to negative 2 plus minus 2i. Square root of negative 4 is 2i over 2. So the total, there are 2 additional roots. So there are 4 roots. The first 2 are from the factors from here. So the root will be 1 plus I, 1 minus I, and then the other root are from here. So -1 plus I and -1 minus I. So there are 4 roots of the equation z 4 plus 4 equals to 0. Three, solve the quadratic equation. So we can find this using the formula again. This is A, B, and C. So z equals to minus b plus minus the root of b squared 4 plus 3i minus 4ac over 2a. So negative 4 plus 3i plus minus square root of. Now we have to calculate this. So this is 16 plus 24i and then minus 3i squared. Square is 9 negative here because I square is negative minus 4 times negative 2 plus 6i minus plus 6i plus I plus 7i and then minus become plus negative 1 negative 3 so become 3 positive 3 over 4 minus 2i. So this equals to negative 4 plus 3i plus minus square root of 16 plus minus 9 is, okay, so 16 minus 9 is 7 plus 24i plus 8 minus 28i minus 12 over 4 minus 2i. So negative 4 plus 3i plus minus square root of 7 plus 8, 7 plus 8, 15, 15 minus 12 is 3 plus minus 4i. So 4 minus 2i. In this case, we have to find the square root of 3 minus 4i. So c squared equals to 3 minus 4i. X plus iy squared equals to 3 minus 4i. So x squared we expand here. Plus 2xyi minus y squared because I squared is also negative here. So 3 minus 4i. So x squared minus y squared plus 2xyi equals to 3 minus 4i. So this is the example to find the square root. So we can use the same method as to find the square root of the complex number. So this is the real part. So x squared minus y squared equals to 3. And 2xy I equals to negative 4. So y equals to negative 2 over x. We ignore the I here. So we replace it to this. So x squared minus negative 2 over x squared equals to 3. So x squared minus 4 over x squared equals to 3. X4 minus 4 minus 3x squared equals to 0. We move the 3x. So x4 minus 3x squared minus 4 equals to 0. So x squared minus 4 plus 1. X squared equals to 4. X equals to 2 or x equals to negative 2. In here, x squared equals to negative 1. So this is not real root, so we can ignore this. And y is negative 1. Y is positive 1. So that means the answer of this is z equals to 2 minus 1i or negative 2 plus 1i. 1i. Or I can say that z is plus minus 2 minus I. So the result of the square root of 3 minus 4i is plus minus 2 minus I. So negative 4 plus 3i over 4 minus 2i. So quite long. So negative 4 plus 3i plus 2 minus I over 4 minus 2i. Or we have negative 4, this bracket, plus 3i minus 2 minus I over 4 minus 2i. For this, we will have negative 4 plus 2 is negative 2. Negative 3 minus 1 is negative 4i over 4 minus 2i. So we multiply with the conjugate, 4 plus 2i, 4 plus 2i. So the denominator will be 4 square plus 2 square. And the top will be negative 8 minus 4i minus 16i minus, so become plus 8. I square is negative 1, don't forget. So this will be negative 20i over 20. So this is minus I. For this, negative 4 minus 2, negative 6. Negative 3 plus 1, negative 2i. Negative 3i plus I is negative 2i over the same 4 minus 2i. So we multiply the conjugate. So the denominator will be the same, 20, and the top will be negative 24 minus 12i minus 8i plus, minus 2 times plus 2 is negative 4i squared, so it's plus 4. So it's negative 20 minus 20i over 20. So it's negative 1 minus I. So the square root, the roots of the quadratic complex number are z equals to negative I or z equals to negative 1, negative I. Polynomial with the given root. So if we know the roots of the polynomial, we can write down the factors and expand this to obtain the polynomial. So this is the same as we did before. So the roots are 1 plus 2i and 1 minus 2i. So the factor will be z minus 1 plus 2i and z plus minus 1 minus 2i. And then we expand z squared minus 1 minus 2iz minus 1 plus 2iz, and then minus become plus 1 plus 2i, 1 minus 2i. So it's equals to z squared minus 1z minus 1z minus 2z, positive 2iz minus 2iz. So we cancel this. And then this become 1 squared plus 2 squared. So plus 5. So this is the final answer. Z squared minus 2z plus 5. This is the exercise you can try for your own practice. Next one is the modulus. The modulus of the complex number is defined by the absolute value of z, and this is z squared, and this is equals to square root of x squared plus y squared. Or we can express it in the multiplication of the complex and its conjugate. For example, find the modulus of this. So this is x, this is y. So modulus of z equals to square root of 3 squared plus negative 4 squared equals to square root of 9 plus 16 equals to square root of 25 equals to 5. So the modulus itself is the length of the complex number from the origin. The distance from the origin to the complex number coordinates. How do we draw the coordinates? We need the diagram, the spatial diagram, to draw the position of the coordinates of the complex number. We call it the Argand diagram. So this is not the Cartesian diagram as we had before, xy, but the Argand diagram is the diagram spatial for the complex number. So we have the real axis on the horizontal axis and imaginary axis on the vertical axis. So x is the real axis and y here is the imaginary, because we have the z equals to x plus iy. So this is x in the horizontal and y in the vertical. And we have r here as the modulus. As I said before, this is the length from the origin to the point of the complex number, the magnitude. And also, we have a theta here that we call it as an argument. So the theta here will be counted from real positive axis, anticlockwise. And we have the negative angle, so that means it's clockwise from the real positive axis. We can express the complex number in the Argand diagram using the polar coordinates. So for example, the complex number 3 plus 4i can be represented on the Argand diagram. It will be in the first quadrant because x is positive 3 and y is positive 4. So I can draw it in the Argand diagram. This is 3 plus 4i. 3 in the x-axis and 4 in the y-axis. So the modulus of the polar coordinate is r or z absolute. So it's 3 square plus 4 square. From here, x square plus y square, yeah, equals to 5. So the length is 5. And the angle that OA makes with the positive real axis is the tangent of y over x. So it's 53.13 degree or 0.927 radians. So the angle here, is found by use the tangent inverse. So like this. The theta is by the inverse tangent of the b over a. So this is the polar coordinates. So we express the z from x plus iy into r and theta. R is the modulus, theta is the argument. How do we find the modulus? By Pythagoras. And how do we find the argument? It's by the tangent inverse. And then how do we write the polar coordinates? Is by changing the x and y. Well, this is a, this is r cos theta, because this is theta, and the y will be r sine theta. So we can replace for the x coordinate is r cos theta, and the y coordinate will be r sine theta. So the polar coordinate can be written in the form of r cos theta plus I sine theta. Some books say this as r cheese theta. Cheese is cos, sine, and I. So cos plus I sine. So that's why we call it cheese. Yeah, well, the r is the modulus and the theta is the argument of the complex number. And we have to remember that the principal argument is always from negative pi until pi. So if we have this is real, and this is imaginary. So the argument of the complex number always from 0 until pi, and negative pi until 0. So this is the theta, or we have, this is the theta. So it's from negative pi to pi, not from 0 to 2 pi. For example, write down the z in the polar form. So we have to find the r. The r here is equals to absolute square root of negative 1 square plus negative 1 square. So square root of 2. And for the theta, it's tangent inverse of negative 1 over negative 1. So this is tangent inverse of 1. So 45 degree. Or in radian, we have pi over 4. But we know that the x is negative and y is negative. So we have negative 1, and 1 is in the third quadrant, which is, it's supposed to be the theta should be the negative. So the theta is not pi over 4, but it should be negative pi plus pi over 4. So equals to negative 3 over 4 pi. So the polar coordinates will be equals to root 2 cos theta. negative 3 over 4 pi plus I sine negative 3 over 4 pi. That's it. This is the exercise. You can try to find the polar coordinate from the given complex number. And this is for the first video, part 1. I will continue the second part in the next video. Bye.